greater distance would lead to far more outs, favoring defensive strategies. The current dimensions represent a finely tuned equilibrium that reflects an understanding of human performance, athleticism, and reaction times. The pitcher's mound itself, with its slope rising 10 inches above the level of the field, creates significant physical effects on the trajectory and velocity of pitches. Engineering the mound's height, placement, and even its composition, such as the type of clay used, are essential for maintaining the desired balance between the pitcher's ability to generate power and the batter's ability to respond. The slight incline generates gravitational force that works in conjunction with the pitcher's throwing motion, allowing for greater pitch velocity due to the added gravitational pull. However, this increased velocity comes at the cost of reduced reaction time for the batter, who must now adjust not only to the speed but also to the subtle downward angle of the pitch as it leaves the pitcher's hand. The height of the mound has even been a subject of engineering and physics debates over the years, leading to regulations that ensure the integrity of gameplay by limiting its height to prevent pitchers from gaining an overwhelming advantage. In lowering the mound slightly in past decades, the governing bodies of baseball essentially recalibrated the physics of pitching to balance both pitcher dominance and batter success. In addition to the mound, the turf and soil composition of the field contribute to the physics of how the ball moves after contact. Natural grass, with its unpredictable blade angles and varying softness, interacts with the ball in ways that artificial turf cannot replicate. Engineers studying the aerodynamics and physics of how the ball rolls or bounces have discovered that grass density, height, and even moisture content have subtle yet measurable effects on ball velocity and trajectory after it hits the ground. For instance, a wetter field introduces higher friction forces, slowing the ball and making it easier for fielders to predict and react to its movement. Drier, firmer turf, by contrast, allows for faster bounces and rolls, challenging infielders with quicker reaction times. Turf design must also account for durability, and the challenge lies in creating a surface that can endure repeated play without significant degradation, ensuring consistent ball behavior over time. The design of outfield walls, another key component of field engineering, also demonstrates the interplay between engineering and physics. The materials used in the wall are weather padded, rigid, or constructed from chain link fencing affect how the ball behaves after being hit. Walls are engineered to absorb some of the kinetic energy of the ball when it makes contact, reducing bounce-back effects and helping prevent excessive ricochets that would disrupt the game. From a physics standpoint, when a ball impacts a solid object, like the outfield wall, a portion of its kinetic energy is transferred into the wall, and how the ball rebounds is governed by the elasticity of the material. A more elastic material would return a higher proportion of energy to the ball, resulting in a longer rebound. By adjusting the materials and structure of outfield walls, engineers can control the amount of energy dissipation and influence how the game progresses. Some stadiums even tailor their walls to create unique quirks in how the ball rebounds, adding a layer of strategy for both outfielders and hitters. Wind and weather conditions also interact with the field's design and the physics of gameplay, especially in open-air stadiums. Engineers consider prevailing wind patterns when designing stadiums, as wind can significantly alter the trajectory of a hit ball. Even subtle differences in the way air flows through the stadium due to architectural elements such as the placement of stands or the height of fences can affect airflow patterns and, consequently, the lift and drag forces acting on a ball. These forces are dictated by the principles of aerodynamics. A well-hit ball traveling through still air might clear the fence easily, while a strong headwind could generate enough drag to keep it in play. Engineers and architects, when designing these open structures, often model wind flow using computational fluid dynamics, CFD, simulations to optimize how air moves through the stadium during different weather conditions. These simulations allow for predictions about how various design elements, such as roof overhangs or gaps in the stands, will affect the game's physics. In fact, Some stadiums are notorious for their wind conditions, where the movement of air across the field has become a strategic consideration for teams. Finally, lighting and acoustics, though often overlooked, are other elements where engineering influences gameplay. The arrangement and design of stadium lights are optimized to eliminate shadows and ensure uniform illumination across the field. This requires careful calculation of the angles and intensity of light needed to avoid casting multiple shadows or areas of uneven brightness, which would impede player performance. In terms of physics, this ties into the inverse square law, where the intensity of light decreases with the square of the distance from its source. Engineers must compensate for this when positioning lights to ensure every part of the field receives the appropriate amount of light, regardless of distance. Acoustically, the architecture of a stadium can either enhance or diminish the ambient sounds of the game. Engineers working with acoustics carefully consider how sound waves will reflect off surfaces, ensuring that the crack of the bat and the roar of the crowd are equally distributed across the field, enhancing the visceral experience of the game while also keeping auditory distractions to a minimum. The baseball field, thus, becomes more than just a venue for play. It is an engineered space where the physics of motion, force, and energy are constantly in motion, all calibrated to create a dynamic, balanced, and fair game. The very concept of a baseball swing, though it appears simple, is a complex dance between physics and biomechanics. From the moment a player begins their swing, multiple engineering principles come into play, such as torque generation, center of mass manipulation, and angular momentum conservation. A player must rotate their body in such a way that maximizes the angular velocity of the bat while maintaining balance. The bat, functioning as a lever, amplifies the player's force, but the skill lies in the precision of the swing path. Engineers who design training tools for batters often focus on fine-tuning the body's rotational mechanics. They consider how the body can optimize the moment of inertia, the resistance of an object to rotational motion during the swing. In physics, this means that players must adjust their body position to either reduce or increase inertia depending on what kind of hit they are aiming for. For example, a compact, quick swing reduces the moment of inertia, allowing for higher bat speed. Conversely, a more extended swing increases inertia but delivers more power if timed correctly. Once contact is made, a new set of physical forces governs the interaction between the bat and the ball. The bat's material, whether wood or metal, significantly affects the energy transfer. Metal bats, for example, tend to have a larger sweet spot due to their elasticity and construction. This increases the likelihood of an elastic collision, where more kinetic energy is transferred to the ball, resulting in a higher exit velocity. In contrast, wooden bats are less elastic and exhibit more inelastic collisions, meaning more of the ball's kinetic energy is absorbed by the bat. This fundamental difference showcases how engineers have to consider material science, another key component of physics. When designing sports equipment, the choice of materials isn't just about performance, it's about safety as well. Metal bats, capable of transferring more energy to the ball, could increase the risk of injuries to fielders, prompting engineers to incorporate safety regulations into their designs, such as limiting the trampoline effect or the enhanced rebound effect caused by certain bat materials. In the outfield, players deal with the ball's complex flight dynamics. The trajectory of a baseball is influenced by both Newtonian mechanics and fluid dynamics, which create a fascinating interplay between gravitational forces, air resistance, and rotational forces. When a ball is hit into the air, its motion can be described by parabolic physics under the influence of gravity. However, the spin imparted during the hit adds a layer of complexity. For example, a ball with top spin will dip more quickly due to increased downward pressure created by the Magnus effect, while a ball with backspin will experience more lift, staying airborne longer. Outfielders must anticipate these physical effects when tracking a fly ball, a split-second decision that involves calculating trajectory, spin, and velocity almost instinctively. In a deeper engineering sense, tracking systems used for player performance analysis are built to capture this precise data, allowing coaches and engineers to model the exact flight path of balls, further enhancing training and strategy development. Furthermore, the role of physics extends to the very surface of the baseball field itself, where friction and surface interactions play critical roles in how ground balls behave. On natural grass, friction between the ball and the blades of grass slows the ball down, while on artificial turf, which is engineered for speed and uniformity, the ball tends to maintain more of its initial velocity. Engineers have taken great care in designing artificial surfaces to replicate the frictional properties of grass, often adjusting the composition of turf materials, fiber length, and infill to provide a more natural feel. This effort is a fine example of engineering's role in balancing the performance of the game with environmental and practical considerations. Artificial surfaces are often chosen for their durability and lower maintenance costs, but they must be engineered to ensure that they do not excessively alter the physics of the game. Even the very air through which the ball travels is subject to scientific scrutiny. Engineers and scientists study atmospheric conditions, such as humidity, air pressure, and temperature, all of which influence how the ball moves. In high-altitude environments, where air pressure is lower, the ball experiences less drag and tends to travel farther. This is one reason why stadiums at higher elevations, like Coors Field in Denver, see more home runs than others. Understanding the physics of aerodynamics in varying atmospheric conditions allows both players and coaches to adjust strategies depending on the environment. Engineers have even designed baseball stadiums with retractable roofs to control the environment inside, reducing the unpredictability of weather conditions. These structures, an engineering marvel in themselves, must balance the structural integrity of the stadium with the need to allow natural light and air circulation when open, all while ensuring player comfort and safety. From an engineering standpoint, the gear worn by players also represents a pinnacle of ergonomic and material innovation. The gloves, helmets, and cleats are all products of advanced material science, where engineers focus on making equipment that is both lightweight and highly protective. Helmets, for instance, are designed using composite materials that can absorb the impact forces of a fast-moving ball, dispersing energy across the helmet's surface to reduce the likelihood of injury. The gloves, often overlooked, are a marvel of ergonomic engineering, crafted to offer maximum flexibility while also providing enough padding and rigidity to catch balls moving at high speeds. Cleats, with their optimized tread patterns, ensure that players have the necessary traction for rapid acceleration and deceleration, accounting for the force of friction between the shoe and the ground. This is an example of how engineering, by focusing on the minutiae of player movement, can optimize performance while minimizing injury risk, another testament to the intertwined relationship between technology, physics, and human athleticism. Ultimately, the game of baseball, though seemingly simple on the surface, is a sophisticated interplay of physics and engineering principles, where every action from the crack of the bat to the arc of the ball in flight is governed by the laws of motion and the intricate designs of engineers. The tools, techniques, and even the environment are carefully crafted, calculated, and calibrated, ensuring that baseball remains a perfect stage where science and sport merge in harmonious balance.